We need to get a grasp of something else as we start dealing with these tiny things. If I have a piece of string and I cut it in half, I can take the half that's left and cut it again, can't I? Right? I'm going to cut that again, and I'm going to cut that in half, right? You'd think that I can always do that. Whatever I have left over, I can cut in half. It might get too small for me to handle conveniently, but at least conceptually, I can go on forever. It turns out that's not true. Because I finally get down to a point of 10 to the minus 33 centimeters. Now, that's very, very tiny. But if I try to cut that in half some way, I discover something very bizarre. It ceases to have locality. It's going to be everywhere at once in the universe. That doesn't mean it's obliterated. Don't misunderstand me. And so there are limits, and it will lose locality. There's a thing called the Planck length. That's 10 to the minus 33 centimeters. There is even a limit to how short a period of time you can have. The smallest unit of time is 10 to the minus 43 seconds. That's not the time that it takes to hit the horn from the guy behind you when the signal changes. That's something altogether different. There is an indivisible unit for length, mass, energy, and time. Everything in the universe is made up of pieces that can't be divided. They're called quanta. That's why the study of this world is called quantum physics. Okay? And the more you know about it, the more ridiculous it becomes. So don't be surprised where we're headed here. Now, as we get underneath the atom and start looking at the parts, we've talked about the nucleus and the electrons floating around it, right? Let's talk about this nucleus a little bit. We used a hydrogen atom, which just has a nucleus, but most atoms consist of a collection of protons and neutrons, right, that make up the nucleus of the atom. Let's take a look at one of these things. Now we're suddenly plunging into the world of subatomic particles. And there's over 200 different kinds that are presently known. And the word known might be a little strong. I'd like to use the word suspected, might be more accurate. But they think they know. Now, most of them are called, the most important ones are hadrons. These are particles which are subject to what I'm going to describe four forces to you. Gravity, electromagnetism, the strong force, and the weak force. The hadrons consist of baryons, which in turn are made up of protons, neutrons, and mesons, and leptons. Now the difference between the hadrons are subject to the strong force, leptons are not subject to the strong force. There are strange neutrinos and quarks. We're going to talk about those just briefly. Relax, these won't be on the quiz, okay? Okay. Each particle that we encounter has an antiparticle, okay? A particle plus an antiparticle results in annihilation plus a photon. Ooh, that's interesting. Now, reversibility could imply that light could have been created out of nothing. Oh, really? Isn't that what the Bible says? That God, Barashit bara Elohim. In the beginning, God created. The word bara means out of nothing. So why should we be surprised when we discover as we get into things that there's always a particle and an antiparticle involved? Ooh, that's kind of interesting. And can it go the other way? Apparently it could at one time. Anyway, as we look at this little hadron, we discover it's made up of quarks. Now these labels were deliberately whimsical. Physicists kept discovering things that they couldn't figure out how to describe, so they started giving them rather whimsical names. So quarks are a deliberate label. And all known particles of matter and energy are classified as hadrons, leptons, or force carriers. There are some particles that are regarded, they are the mechanism by which forces are exerted. And so we have hadrons, leptons, and force carriers. Scientists believe that leptons and force carriers are fundamental particles, meaning they cannot be divided into smaller particles. And yet, we'll take a look at some of this. The most common hadrons are protons and neutrons. You've probably run into those in school in chemistry, making up a nucleus. Protons and neutrons. They're the building blocks of the nucleus of an atom. Hadrons have an underlying structure of smaller particles called quarks. We'll talk a little bit about quarks There are all kinds. They're labeled up, down, charm, and strange. Doesn't mean they're up or down. Those are just labels that, out of frustration, physicists assigned them for some they each have some very peculiar characteristics. There are 6 different quarks listed there. It gets worse because there's anti-quarks also, because there's an anti-up and an anti-down, and those are not opposites exactly. Anti-charm, anti-strange, anti-top, and anti-bottom. And if nothing else, this briefing will probably result in a resolve never to get into quantum physics, because it is a strange world for lots of other reasons too. So quarks have these strange names. They're represented by different symbols. Each has a different mass at rest, everywhere from just a few hundred million electron volts to over 22,000 million electron volts. And so they all they're actually quite different. And their electrical charges are in fractions. That doesn't bother you weren't listening carefully. You know, electrical charge is 2/3 or minus 1/3 and so forth. Okay. It gets worse, okay? The study of these, since they started giving these quarks names as colors, don't think they're colored. These are just labels, okay? And so they have colors, red, blue, green, and they're always combined. The elements are combined so that collectively with some other things they're colorless. So these are they have self-balancing aspects to them. But these are not colors as you and I use them. These are colors. These are labels of particular kinds of quarks, and so I call them pigments of their imagination. Okay. So we have red, blue, and green. In certain conditions, they're neutralized to make them colorless, which means it's balanced. That's just the labels they've used to represent those particular kind of quarks. Now, there's also anticolors. There's anti-red, sometimes called cyan, anti-blue, which is called yellow, what you call it yellow, anti-green, which is magenta. That's another 3 to make 6. Okay? So you've got magenta, yellow, cyan. You ready for this? On certain occasions, you want to combine those. Yeah, isn't that interesting? And that makes it balanced. And we'll talk a little bit more. This field of study is called chromodynamics, because they're using colors as labels, not as colors. Don't confuse this with light and the fact that red, blue, and white, you make white. That's a whole other thing. All known hadrons are colorless, meaning their collective quark situation is totally neutralized to be colorless. That's one of the reasons they use colors, to get across that property, if you will.